This is the fourth calculus video, and we're going to be looking at sketching cubic functions. But just before we actually start sketching them, I just want to show you a few of the various cubic functions you can get and how different they may look. So you get cubic functions that only have one x-intercept, and here are two examples. Notice in this case that the format of the function was officially ax cubed. In the first one, a is equal to 1, and in the second one, a is equal to minus 1. So when you see an equation in that format, you can know immediately that there is only going to be one x-intercept. And notice that when the a is positive, then the function is starting increasing, and when the a is negative, negative 1, it's a decreasing function. Okay, now let's have a look at what a cubic graph looks like if it has two x-intercepts. So we have an x-intercept here and we have an x-intercept here, but notice something interesting happens at this x-intercept. It also happens to be a turning point. That is something that we'll discuss in more detail later. But if a cubic function has two x-intercepts, then one of them will be a turning point. We also have three x-intercept possible. That's probably the more obvious one, I think, when you see that it's a cubic function. So you can also have your three x-intercepts. So what I wanted to say about this one as well that I forgot to say. If you are drawing this function from the left, you'll see it starts by decreasing, and then it will increase a bit to the next turning point, and then it decreases. Because it starts by decreasing this one, a would have been negative. So the number in front of the x cubed term would be a negative. In this case, we start by increasing, so we already know that a is positive. At the turning point, it will then decrease, and at the next turning point, it will increase again. So this is one of the examples we just looked at. When there are two turning points on a cubic function, we call them the local minimum and the local maximum. But you can't just say that it is a maximum or a minimum point, because as you can see, that is not the maximum point, because this function goes there as well, and the same story with this is not the minimum. The function continues in that direction. So the two turning points, one of them will be called a local minimum and the other one is a local maximum. The official name we should actually be using rather than a turning point is a stationary point. Maybe we just need to talk about those two words for a second. So a stationary point is a point on the function where the gradient of the function is 0. So hence you can see that these two are stationary points because the gradient, remember the derivative, the gradient of this tangent line would be 0. A turning point is a point at which the graph changes from increasing to decreasing or decreasing to increasing. So you can also see why this is a turning point. First it's decreasing, and at that turning point it then starts increasing. And then at this turning point it then starts decreasing. So a turning point is always a stationary point. Think about that for a second. A turning point, what you see here, is always a stationary point. A stationary point is not always a turning point though. It could be a point of inflection. So just to take you back, this is a stationary point, but yeah, I'm sure you can see clearly that it is not a turning point. Now I'd like you to consider this point here, 0, 2, and then imagine drawing this cubic function. So as I'm going downhill here and at the turning point I come uphill, at that point you'll see you now suddenly going in you're almost drawing in the beginning you're almost drawing a positive parabola versus a negative parabola, but I don't want you to think of the cubic function as two parabolas because it's not. I was just thinking from a drawing point of view. Like here I could maybe be drawing the beginning of a positive parabola, but at this point I suddenly start drawing the negative one. So this point is also a key part of a cubic function, It's called the point of inflection. And that is where a function changes from concave up to concave down, or vice versa. So we have concave up and we have concave down. And the point of inflection is where it would change from the one to the other. So when you are drawing this part that could hold water, so it's like a cup, so therefore it's concave up, at this point now you're suddenly drawing a concave down part of the cubic function. This is maybe a better diagram of that. So the inflection point is where the cubic function changes from concave up to concave down, or the other way around, because if it had been an increasing function, perhaps that wasn't a very good function, sorry, perhaps that would be the point of inflection. Then notice it's changing from concave down, the point of inflection then changes it to concave up. So to draw a function, the 5 points on the left-hand side are what you need to be looking for. First, decide on the shape. So if the a is positive, in other words, if it maybe starts with 2x cubed and continues, a is positive, then you know that it is going to increase first. So this one would increase first, so it would end up looking like that. If a is negative, on the other hand, so maybe there's a negative x cubed and then it continues, that's going to go downhill first and then. So always decide on the shape. It's good to have the idea of the shape in your mind, because once you put all the points you need on a Cartesian plane, sometimes it can look a bit confusing about how you're going to join them. Once you've decided on the shape, and that's a good idea to draw that little sketch, you're going to find both the x-intercepts and the y-intercept. We find the y-intercept by making x 0, just as with any other function, and you find the x-intercepts by making y 0. And then you find the stationary points. To find the stationary point, you find the derivative. So you're going to use your rule and find the derivative. You're going to make it equal to 0. Because the stationary points you're looking for at the moment are the turning points. And remember that at a turning point, the gradient of the tangent would be 0. So that is why we're making it equal to 0, the derivative. Make it equal to 0 and solve for x. But then you'll only have the x coordinates of the turning points. So therefore you need to substitute those x coordinates back into the original function you were given in order to find the y coordinate. So that you will then find that if there are 2, you will find those 2 coordinates, which will give you the turning point. Finally, you're going to find the point of inflection, so that you can see where the function changes from concave up to concave down, or vice versa. And to do that, you find the second derivative, which means the derivative of the derivative. So you just perform the rules as you do usually, the derivative of the derivative function. Again, make it equal to 0 and solve for x, and again substitute the x value back into the original function in order to find the y value. So we're going to do a few examples together now, and we'll keep on looking at all those, keep going back to those points and what we said. So the first point was to decide on the shape. In this case, the a value is a 1, it's a positive 1. So because a is positive, I'm expecting my function to increase first. So that's what the shape of this function will look like. Then we're going to look for the y-intercept, and we find the y-intercept by making x equal to 0. So y is equal to minus 2. So the y-intercept is 0 minus 2. Then we're going to look for the x-intercepts, and we do that by making y 0. You may need the factor theorem here. If it factorizes, and in this case it does, we can group it. In the first 2 terms there's a common factor of x squared, and I can take negative 1 out, so I'll have x plus 2 left there as well. In the 2 terms I have left, x plus 2 is a common factor, and x squared minus 1 is what is left over. X squared minus 1 factorizes further, it's a difference of 2 squares. And you can see I have 3 factors, so therefore there are 3 x-intercepts. Either x plus 2 is equal to 0, so x is negative 2. Or x plus 1 could also be 0, so x is negative 1. X minus 1 is 0, so x is 1. So our x-intercepts are negative 2, 0, negative 1, 0, and 1, 0. Now we're going to find our stationary point, so we're looking for the derivative of the function. I hope by now doing the rule is pretty easy for you. So that's what you should get for the derivative function. We make this equal to 0 because we know that the gradient at a turning point is 0. Now we're going to solve for x, and as you can see it's a quadratic, so we're expecting two solutions. This doesn't happen to factorize, so therefore don't forget you can use the quadratic formula when it doesn't factorize. And that is on your formula sheet, and then you can use your calculator. I'm just going to give you the solutions. X is 0, 2, or x is negative 1, 5. I need the y coordinates. These are my x coordinates of the turning points, but I need to find my corresponding y coordinates. Sorry, what I did there, put the semicolon twice. To do that, I need to put each one back into the original function. Remember, that is where the coordinate lies, on the original function. So I'll first put the 0, 2 in. If I do that calculation, I will find that it is negative 2, 1. And then I substitute negative 1, 5. And you can be doing all this work on your calculator. Negative and negative make a positive. And that gives me 0, 6. So I have found the coordinates of the turning point. Finally, let me just write the derivative here again. I shouldn't have erased it. Finally, I'm now going to find the point of inflection. So I find the second derivative, or the double derivative. So 2 times 3 is 6, and with the x to the power of 1, and that will just be 4. Make it equal to 0. Solve for x. Subtract 4 from both sides. Divide both sides by 6. And simplify if possible. Again, I now know the x-coordinate of the point of inflection. I need to find the corresponding y-coordinate. So f of minus 2/3 into the original function. Plus 2/3, because the negative and the negative make a positive. And you will put all that into your calculator, and it will give you negative 0, 7. And we now have the point of inflection. So just to recap what each of these are. So we have our y-intercept, one of them. We have our x-intercepts. We have the coordinates of the turning points, and we have our point of inflection. So you're now going to plot all of those points onto your Cartesian plane, marking each coordinate off. And then don't forget to look back here to see that you're definitely coming in from the left bottom, so you start increasing, in other words. And then you can see here I have that function. This particular drawing doesn't show all the markings. Maybe we should fill them in. So we've got our 3x intercepts there and our y-intercept marked. But our turning point was 0, 2 and negative 2, 1. So that was this one here. 0, 2 and negative 2, 1. The other turning point, negative 1, 5, 0, 6. So negative 1, 5 and 0, 6. And our point of inflection, negative 2/3, negative 0, 7. So negative 2/3, negative 0,7 would be around about there. So that's our point of inflection, and remember what happens there. This is so far concave down, and at the point of inflection it becomes concave up. Let's do a second example. Again, let's go through all the steps that we have to do. The coefficient of x cubed is negative. So therefore, because a is negative, it's less than 0, this function is going to decrease first, so it's going to look like that. We find the y-intercept by making x 0, and if you make x 0, you can see that the only term left would be y equals 2, so the y-intercept is 0, 2. So there's our first step, there's our second step, the y-intercept. To find the x-intercept, we make y equal to 0. I'm going to take a negative out. You would need to use the factor theorem here to find the first factor. So you would be substituting 1 and then negative 1 and 2 and negative 2 until you got 0. And for example, if 2 made it equal to 0, which what this one does, if I substitute 2 in, I get 0. So that means that x minus 2 is a factor. Because remember what happens when you factorized and you get x plus 2x, for example. Let me just write that down instead of just trying to say. Say you had got this when you were doing a quadratic and making it equal to 0. Remember that the factor of x plus 2 equals 0 gives us a solution of minus 2. So once you've found out what number makes it equal to 0, you've got to remember to undo that to make it into a factor. So in this case, x equals 2 works. If I make x equal to 2, then the function will equal 0. So therefore, x minus 2 is a factor. Once you know that, you'll then have to use division to find the other factors, or well, to first find the remainder, which would be that. And then you will factorize, and you will see that this happens to be a repeated factor because it's a perfect square trinomial. So I mentioned this earlier. So first of all, remember we're only going to get 2 x-intercepts here. And keep in mind that the repeated factor also means that the turning point will happen at that x-intercept. We're still going to work the turning points out though, and then you can just confirm that that is correct. So our x-intercepts are 2, 0 and negative 1, 0. We're now going to find the turning points. And remember how we do that. We find the derivative of the function. We make it equal to 0 because we know that the gradient of the tangent at the turning point will be 0, and we solve for x. So to the derivative of the function minus 3x squared plus 3, make it equal to 0. I can take out a common factor of negative 3, so I'm left with x squared minus 1, which then factorizes as a difference of 2 squares. If I could divide by negative 3 on both sides now, the negative 3 is not going to affect the solutions we get. So x plus 1 is equal to 0. So there's a turning point when x is minus 1. And x minus 1 is equal to 0, so there's a turning point where x is equal to 1. Don't forget we actually already found one of those. But now we need to find the y-coordinate of those turning points. So we go back to our function to find the y number. So y is equal to, I'm first going to put the negative 1 in. And if you do that calculation, you should get 0. which I think you should have known from looking at that. We're expecting that x-intercept to be our turning point. And then we're going to put our 1 in. I forgot the negative there. And that is equal to 4. So 1, 4 is our other turning point. Final step. We're now going to find the point of inflection. So we're finding the double derivative. Note how I set that out. 2 multiplied by -3. Make that equal to 0. And solve for x. Divide both sides by -6. To find the rest of the point of inflection, I need to substitute that back in. And if you look further up, I think you'll already know what it is. If you look up the left-hand side, let's do the calculation. And that is equal to 0. Sorry. What am I doing? Apologies. I was so busy thinking the answer was 2, I put it in. Apologies. So I am putting 0 into x's place. And that is equal to 2. And you'll notice that it also happens to be the y-intercept. So we're now going to plot this. I have the diagram again for you. There are your 2 x-intercepts. Remember, the one of them happens to also be a turning point. There's the other turning point. There's the y-intercept and the point of inflection. So it was decreasing until this turning point, and then the function is increasing until that turning point, and then it is decreasing. Over and above that, the function is concave up until the point of inflection, and then it becomes concave down. Okay, let's look at a final example. We're going to do this with all the steps, even though some of you may already know what it looks like, but I'm going to practice those steps again. So the a value, in other words the coefficient of x cubed, is positive. So therefore we are expecting our function to increase first. At this stage you need to know that it's not going to do that. If you're not so sure yet, that's okay, but it is still increasing first. So I'm going to keep my increasing part there. Now let's find our y-intercept, and we find our y-intercept by making x 0. So y is equal to 1. So when x is 0, y is equal to 1. Now we're going to find our x-intercepts, or intercept, we will see, by making y 0. I think it might be better if we write it this way around. You don't have to, of course, and we could have easily had it the other way, but I think it's easy, and you know they're both positive. Just remember the sign in front of a term belongs to it, so when you move it, do check that out. This is the sum of 2 cubes. Cube root each term and keep the sign. Square the first term, square the second term to get the last term here. Multiply the 2 terms in the first bracket together, but change the sign. So if x plus 1 is equal to 0, this does not factorize, but I'll get to that in a second, then x is equal to -1. So -1, 0 is an x-intercept. The other side is interesting because x squared minus x plus 1 does not have any real solutions. Because it doesn't factorize, you may have looked at the quadratic formula, and the quadratic formula with the solution on the calculator would be, well, there wouldn't be a solution. They would be telling you that there are no solutions. So because x squared minus x plus 1 has no real solutions, this is the only x-intercept. Let's go on to the next stage. We're now looking for the stationary points. So we need to find the derivative of the function. The first term is a constant, so that's 0. So it's just the second term that we have that for. And then we make this equal to 0. Divide both sides by 3. And I'm sure you can see that x is equal to 0. That gives us our x coordinate of the point of inflection. I think if you look on the left-hand side, you'll see that you should already know what the y coordinate is. But in general, we would be substituting that back in to find the corresponding y number. So can you see it also happens to be the y-intercept is also your stationary point. And finally, we're going to find or look for the second derivative in order to find the point of inflection. So that is 6x, make it equal to 0, and solve for x. When x is 0, I think we already know that y is 1. So you're going to have to get used to these functions, and I think the more you draw, the easier it will be for you to notice. But the problem with this is you can see that you actually only have 2 points on the function. You only have -1, 0 and 0, 1. And the 0, 1 is where many important things are happening according to the function. So that's another reason you definitely need to know whether you're starting with it increasing or decreasing. And remember, a was positive, so we're definitely increasing first and going through those 2 points. You might want to substitute an x coordinate into the function. You know, maybe you could have put 1 in to find another point just to help you make sure it looks a little bit more accurate. So the point of inflection on a function like this one can also be called the horizontal inflection. But that was our third and final example. So that brings us to the end of this video. Our next video we're going to be finding the equations of cubic functions. So we'll be working this in reverse. We'll be given information about it or given the diagram, and we'll have to find out what the equation is.